Hello, everyone. Okay. My name is Tomasz Kostecki, and I'm a medical physicist at Diagnomatic. I've been working with MRI scanners for about 15 years, and I would like to welcome you to this presentation. Today, I would like to share a practical introduction to MRI quality control, focusing mainly on American College of Radiology routine constancy testing. I will explain which diagnostic products can be used. I will go through the main test procedures and then briefly talk about Diagnomatic Online. All the tests are explained in the 2015 manual. It is free to download from the ACR pages. Diagnomatic provides 4 types of MRI phantoms, 2 Pro-MRI ACR Phantoms, certified for use with the American College of Radiology accreditation program, and 2 older Pro-MRI Phantoms. At first glance, they look similar. So here I'll show the main difference and how to recognize which phantoms you are using. This is important because customers sometimes confuse the Pro-MRI and Pro-MRI ACR Phantoms. If the wrong phantom type is used, the test procedure might not work as expected. So this table compares the 4 MRI phantoms available from Diagnomatic. The older Pro-MRI phantoms have a slightly different design, including more vials and additional wedge structures, but they can still be useful for routine quality control. The main difference is the diameter of the phantoms. The Pro-MRI ACR phantoms are also ACR-approved, which means they can be used for ACR-MRI accreditation as well. So if you see the sagittal localizer with 2 wedges, you know that you are not using the ACR phantom. And so here we have 2 pairs of wedges. Now, from this point onward, I will focus only on the ACR phantoms. As shown in the table, ACR phantoms are available in 3 sizes: large, medium, and also small. Diagnomatic is currently working on the small one, so it will be available soon. This table shows how to select the right phantom for a particular MRI site. The general rule is to use the largest ACR phantom that fits inside the head coil used for clinical brain imaging. So if a large phantom fits your normal brain coil, you use the large phantom. If it doesn't fit, you use the medium phantom. If the medium phantom doesn't go into your head coil, use the largest phantom that can fit in an alternative clinical head coil. The main difference between the Pro-MRI ACR phantoms is their size. Because the medium phantom has a smaller internal volume, some of its internal structures are shortened compared with the large phantom. Basically, each element of the large phantom is cramped inside the medium one. So as you can see on the left, in the upper part of the image, the corners of the wedges are cut, but it doesn't change anything. Both phantoms can be scanned using the same general protocol, including the same number of slices, field of view, and slice thickness. It all depends on the coil size which you are using. The ACR MRI system performance evaluation includes both weekly and annual quality control tests. In this webinar, we will focus mainly on the tests that can be demonstrated using the Pro-MRI ACR Phantom, such as geometric accuracy, high contrast spatial resolution, slice position accuracy, slice thickness accuracy, and RF coil checks. The most crucial and often most time-consuming part of the procedure is correct phantom positioning. Diagnomatic provides several positioning aids to make this step easier and more reproducible. These include a spirit level, mounting shelves for the levels, and dedicated cradle. The cradle can be slid directly into the head coil, reducing the need to immobilize the Phantom with pads or sandbags. This makes positioning faster, more stable, and more consistent from one quality control session to the next. This image shows how the Phantom interior elements can be used for alignment. The Phantom is correctly positioned when the laser light is aligned with the superior edge of the grid structure or geometry block, like in the middle picture. If the laser is properly calibrated, this alignment will place the Phantom correctly at the magnet isocenter after it is moved into the scanning position. Okay, so as you can see, we place the laser just so it touches the grid. After positioning the Phantom, we can start the scan. First, we perform a standard 3-plane localizer to check the general position and alignment of the Phantom. After that, we perform the first ACR sequence, the sagittal localizer. It is important to remember that the 3-plane localizer cannot replace the ACR sagittal localizer. The first localizer images do not have sufficient spatial resolution for accurate axial slice prescription, Phantom length measurement, or table position evaluation. Also, the sagittal localizer is used in our software for setup and geometry tests. You can use slice thickness 20 or 10 millimeters, and then that depends on you. We usually use 20 millimeter thickness. Okay, let's start with the tests. The ACR provides a weekly quality control data form to help record the test results in a consistent way. This makes it easier to compare results over time and identify changes in scanner performance. The first test in this form is setup and table position accuracy. To perform this test, we use the ACR sagittal localizer image. If the positioning laser is correctly calibrated and the table positioning system is working properly, the superior edge of the geometry module should be located at the magnet isocenter. That is why we place the laser here, right? So we place the laser on the top of the geometry block, and then we check the isocenter of the magnet. Where does it show 0 on the image? If this value is within the accepted tolerance, the table position accuracy is considered acceptable. So it's 5 millimeters. You can move plus or minus 5 millimeters. Further tests are assessed using the axial scans of the Phantom. ACR accreditation uses several Phantom sequences shown here. You can save them in your scanner as ACR test sequences, like we did. For weekly constancy checks, the ACR manual recommends using the ACR sagittal localizer and the ACR axial T1 weighted sequence. You can also add your own sequences as you wish. The next step is to plan the axial series on the sagittal localizer. The ACR protocol uses 11 axial slices. These slices should be positioned carefully using the centers of the slice locations and not the slice outlines. Right, so it sometimes happens on Siemens that we have two lines instead of one in the middle. Correct slice positioning is important because different quality control tests are performed on specific slices. If the slices are shifted or tilted, the measurements might fail even if the scanner itself is working correctly. The basic slice should be positioned at the inferior wedge, close to the chin of the phantom. In the ACR description, this is usually treated as slice 1. However, depending on the scanner system and the direction in which slices are numbered, the same physical slice might appear as slice 11 on your console. A simple way to check correct positioning is to look at the first slice, the resolution slice. The two wedge structures should appear at the same height, like here. If they are not equal, the slice position or phantom alignment might need correction. This is an exaggerated version, so once one side of this object might be longer than the other, then you should correct it. On the first slice of the ACR Axial T1 series, we can test high contrast spatial resolution. This test checks whether the scanner can distinguish small structures that are close together. Note that the large medium ACR phantoms and medium ACR phantoms have different number of resolution arrays. The large phantom contains 3 arrays, while the medium phantom contains 4 arrays. The arrays are made of small holes grouped in pairs. The biggest holes are 11 millimeters, 1.1 millimeter, while the smallest are 0.8 in diameter. Each pair has an upper left array called the UL and the lower right array called LR. The UL and LR arrays meet at the one corner and share one hole. The UL array is used to assess the resolution in the right-left direction, while the LR array is used to assess a resolution in the top-bottom direction. So in practice, we check both directions to confirm that spatial resolution is stable. The image passes if all 4 holes are distinguishable in one column of the lower right array and one row of the upper left array at the tested hole size. So this is a blurred image, but it usually looks like that, right? The measured resolution might be different in the top, bottom, and the left to right directions, right? So I found this set of holes here, and I found this set of holes here, but I cannot find 4 holes here. Because this is a visual test, the result depends partially on the observer's judgment, window and level settings, and display conditions. Next on the same slides is the slice thickness accuracy test. This test checks whether the measured slice thickness matches the prescribed slice thickness. It is performed using 2 crossed signal ramps. The ramps are inclined at a 10:1 slope, so the visible ramp length is related to the actual slice thickness. The process for setting the window level has 6 steps, and we will get back to it when we will talk about the diagnostic software. Geometric accuracy. Geometric accuracy is performed on slice 5, the middle of the phantom, and the ACR sagittal image. It tells us whether the scanner measures distance correctly. This is of course important clinically because if the geometry is wrong, then for example a tumor measured with the system ruler might appear larger or smaller than it really is. During follow-up diagnostic imaging, this could influence the assessment of progression or remission. Low contrast detectability, LCD for short, is based on slices 8 to 11 of the ACR Phantom. The test objects are small low-contrast discs arranged in the spokes of like the spokes of a wheel. Each spoke contains 3 discs, and each circle contains 10 spokes with contrast ranging from 1.4% to 5.1%. It's very important that once the window and level are established for specific scanner and slice number, they remain the same from week to week. The medical physicist selects the slice that is most sensitive to changes in scanner performance, and then this disk is evaluated weekly. Low contrast detectability is then assessed by counting the number of complete visible spokes on the selected axial slice. Note that this test is very positioning sensitive, as if you, for example, angle the slices too much, some of the spokes might not be visible at all or on all of the images, right? So those spokes that are located, for example, here, might not be visible at all. But then again, the smaller ones can be visible as they are still on the same slice. Slice position accuracy. Slice position accuracy, we measure the length of the wedges on slice 1 and 11. If one bar is longer than the other, the slice is displaced superiorly or inferiorly. The bar length difference is measured and used to estimate the slice position error. So this is the first slice, and the one we set up at the beginning, and then we check the differences on the 11th slice. The next group of annual tests is the radio frequency quality checks. A useful practical point is that sagittal to noise ratio, percent image uniformity, and percent signal ghosting can all be evaluated on the same central uniform slice. In the Pro-MRI ACR Phantom workflow, this is usually slice 7 of the ACR T1 series. The slice is the same, but the ROIs and the purpose of each measurement is different. Right? So here we have the percent image uniformity. We have to take 2 ROIs. In the dark region and in the white region. In the percent signal ghosting, we place 4 additional ROIs, and for signal to noise ratio, we just calculate those 3 ROIs. The last part is the software. The quality control is about recording the result. This is not only about writing down a number. For testing purposes, we should keep the images, measurements, ROI placement, scanner information, coil information, phantom information, and final results together. A good quality control record should answer 3 questions. What was measured? how it was measured, and how it compares with the previous results. This is why, if you are interested in Pro-MRI ACR Phantoms, I also encourage you to consider Diagnomatic online software. And one more thing. As promised, here is the sixth step procedure for measuring the ramps used in the slice thickness accuracy test. When you see how much manual work is involved, it becomes clear why this is an annual test rather than a weekly quality control test. This is also where Diagnomatic software can help. It really reduces a lot of manual work and also limits user bias. This makes testing faster, more consistent, and easier to review next time you are doing quality control. And also for enthusiasts, we provide the reports in Excel format. Okay, thank you for your attention. I will be happy to answer any questions.
Thanks, Tomasz. I think I'll bring up my presentation and then we can do Q&A at the end if that's okay with everybody. Yeah. So again, thank you, Tomasz, for your presentation. It was really interesting to see the Diagnomatic product, especially for diagnostic MR QA. Hello, everyone. My name is Umar Baharom, and I'm the product manager and OEM strategic accounts at Standard Imaging. And I just follow up with what Tomasz has done on his Phantom lines and talk about the MRgRT Phantom. So I mean, I think most of us know the benefits of MR in for radiation therapy. It's been used for so many years now. Obviously, it's becoming more and more prevalent in this field. Just kind of reminder, what's the benefit of the MR in radiation therapy, right? It's superior in terms of soft tissue differentiation versus CT, and also there's no ionizing radiation. It's just kind of a good image to see the difference here. And then in radiation therapy itself, there's really kind of two main uses of MR. This MR-guided radiation therapy, where you have vendors and machines such as the ViewRay Meridian, which is a 0.35 Tesla, has a split magnet, 70 centimeter bore, 6 NV triple F, and a high resolution MLC. And then the next one is the Elekta Unity at 1.5 Tesla. Also, the next one is for MR simulation, where traditionally is MR-CT fusion, but more and more now you'll see MR-only sim, kind of converting that into a synthetic CT for planning. So there is one issue. Well, one of the issue with MR is geometric distortion. And it's really the distortion because of the magnetic field. When we're talking about MRs, these are the main causes, right? There's the gradient nonlinearity, there's the B0 inhomogeneity, and some susceptibility effects based on different tissues in the human body. Here you see what it will look like without kind of a distortion correction on the left side. And then what it looks like with the distortion correction. And obviously in radiation therapy, spatial uniformity and accuracy is very important, especially targeting for the tumor and sparing of the critical organs. So the vendors for MR vendors, they usually provide distortion correction with the software, but there's still some residual distortion that you can see even with the distortion correction turned on. So it's still very important to kind of verify and perform a QA. I'm just kind of referencing APM TG 286 for MR statement RT if you want to take a look at that some more. So this is the Phantom, kind of a scan of the Phantom. We design and manufacture the Phantom for large field distortion. Again, as you know, for MR, most of the distortion is going to be happening in the far field, right? In the center is a little bit, it's more uniform, but as you move away from the center, that's when you get a lot of distortion. You kind of see here in this image here on the side. So again, the MR grid is designed for a large field MR distortion assessment. You use it to verify your image distortion in 3 axes. So you know, there is you know, X, Y, Z. Obviously, in terms of the coverage, in terms of the bore size is large, but there's also some coverage over the Z axis as well. It's comprised of 9 imaging planes, right? And it's made out of these grids. And we have over 4,000 individual you know, spheres that you can see. So you can evaluate the distortion in axial, sagittal, and coronal planes. And the Phantom is made out of acrylic, and then this carries strap included as well, because Phantom is fairly heavy. Here are the dimensions. You know, 500 millimeter in diameter, and you know, 380 in height. The spheres are 8 millimeter in diameter, and the center distance is 16 millimeters. And then again, like I said, it's made fully acrylic, and the fill solution is a 0.4 millimolar nickel chloride. And the Phantom comes pre-filled. You don't have to do any filling. You know, if you do need to refill the Phantom in the future, if you lose any liquid, then we can provide the you know, refill kit as well. Some of the scan sequences, here's some that we've done in the past. So T1 3D Vibe, T1 3D Vibe Dixon, T2 Space, and T2 weighted TSC. Here you can kind of see the construction of the Phantom. It's basically an acrylic tank, and then we have these plates. We have 10 plates, and then in each plate we machined out a kind of a hollow sphere, and then that's filled in with the liquid. So we do, there's quite a bit of assembly in terms of the Phantom to remove a lot of air bubbles as well. So there's, you know, very minimal air bubbles in the Phantom. So the Phantom comes with the software as well. So this is the IQA software analysis. Basically, again, with the distortion, we're just kind of looking at the areas where you will see any issues. So you kind of see kind of a heat map. You know, within a certain, you know, if this the point errors is within 3 millimeters, you know, for this particular scanner, you know, 98% of it is within that. As you can go here is within 1 millimeter, you know, it's mostly about 65%. So there's a lot of distortion here that's beyond 1 millimeter, as you can see. So again, for the applications for the MR Phantom, it's really for your commissioning and QA. If you want to compare your MR kind of distortion map versus a CT, so you can CT the Phantom as well, and then you can kind of do the comparison. You want to assess your maximum and mean deviation for your clinically relevant regions. So for APM TG 286, you want to be under 2 millimeter, you know, within the 20 centimeter field of view. You also want to establish a baseline for your scanner. So you want to track any drifts or hardware issues in the future. So in terms of the usage kind of frequency, I think most sites will use it at least once a month. They'll do more intensive QA yearly. Risk assessment and margin evaluation. So you know, if you know where the areas there are have a little bit more distortion, so then you can expand your target and organize risk margins, right, to compensate for the, you know, worst case distortion within that region. So yeah, if you, again, within the brain, again, the center of the bore, it's a bit more uniform. So you want to be, you know, within 1 millimeter. Again, if it's within 1 millimeter, then you don't need any more extra margin. But if it's, you know, 2 or 3 near the periphery, you may want to add some PTP margin there. So field view optimization, you know, again, like I said, distortion increases towards the edge. So if you see a lot of distortions, you may want to limit your field view during the scan. So there's a cross-modality validation as well. So you can use the distortion map to validate your registration between MR and CT, you know, like I talked about earlier with decommissioning QA. You can also quantify the residual misalignment attributable to the MR distortion versus your registration error. So yeah, that's pretty quick on the MRgRT Phantom. It's much more simple than the for diagnostic. It's really just for your large field MR distortion. So I think we're coming to the end here. So I'll take any questions you have of my presentation, and Thomas, feel free to type it into the chat, and then we'll do our best to answer those.
Okay, so as I understand, someone is asking about the Phantom with 6 vials, right?
Yes.
So this is the old Pro-MRI Phantom from Diagnomatic, and it was just for routine quality control, right? So it was just for checking if the system still shows the vials as it was on the beginning. The minimal values are known, and they are shown in the manual. As for the system, it just takes the MRI images, and it produces the values that are in the captured in the area of the vials. So if the MRI is set, for example, to show the T2 images, the vials will be white. So I guess it will show some number. And then when you check it in the next week, you just check if the MRI produces the same value. Okay.
Do you have any reference T1 and T2 values for the liquids in the vials?
No, we don't have the reference values.
Okay. And there was another question on so the resolution of the MRgRT Phantom. So again, the resolution of the fiducials themselves is 16 millimeters. So that's the resolution of the dots itself. So in terms of the software analysis, it's about 0.2 millimeters. That's the kind of the resolution that you can detect. Hope that answer your question. All right. Here you go. You can use sales at standard. Yeah, okay. Ashley is addressing it. All right. Thank you, Ashley. Again, thank you so much for joining the webinar. You can always go to our website or Diagnomatic's website to find out more information. But yeah, if you have any specific questions on the Phantom, on the MRgRT, you can feel free to reach my email here. But in general question in terms of sales, here's the email for sales as well. All right, thank you, everyone.